In this video, I'm going to give you some tips for solving the ALEKS problem called predicting the strength of intermolecular forces from an electrostatic potential map. This problem is going to give us 4 different molecules represented by electrostatic potential maps, and our job is to rank those 4 molecules based on their intermolecular forces. We're going to take a few things into consideration when we're doing this ranking. Number 1, we're going to take the size of the molecule into consideration. I've looked at quite a few versions of this ALEKS problem, and all of the molecules seem to have 2, 3, or 4 different atoms in them. So that's going to be one of the variables that we consider. We're also going to be considering the depth of the coloring and the electrostatic potential map. So for example, this one has pretty dark colors. This one has faded color, and these ones have no coloration at all. We're going to take that into consideration as well. But the very first thing that we're going to take into consideration is symmetry. Molecules that have that are symmetrical. So symmetrical. These molecules have low or weak intermolecular forces, and molecules that are asymmetrical, that do not have symmetry, these are the ones that are going to have the higher or stronger intermolecular forces. So we're looking for a really specific type of symmetry in these molecules because, so first of all of the problems that I saw, they all have their molecules oriented in this same order with the atoms kind of going from top to bottom. None of them are looking like this. So what we're looking for specifically is top to bottom symmetry, where this I'm calling the top of the molecule and this is the bottom of the molecule. What we want to do is find that line of symmetry that divides the molecule in half from top to bottom. So we're specifically looking at that plane of symmetry. We're not going to be thinking about this plane of symmetry. All of the molecules are going to be symmetrical along this particular line. So we want to look at this line right here, dividing the molecule from the top half to bottom half. Is the molecule symmetrical across the top and bottom half? This one is. The top half is identical to the bottom half. This one also, the top half is identical to the bottom half. This molecule is also identical, top half, bottom half. The outside of the molecule is red. The inside of the molecule is blue. As we go from the top to the line of symmetry, we go from red to blue. As we go from the bottom towards that line of symmetry, we go from red to blue. So this one is symmetrical as well. This one is not. This one is red on the top and blue on the bottom. This is an asymmetrical molecule. The asymmetrical molecules are the ones that have the highest or strongest intermolecular forces. We only have one. I'm going to use the letter A for asymmetrical, symmetrical, symmetrical, symmetrical. We only have one, and ALEKS is going with number 1 for the molecule that has the highest intermolecular forces. Now, just in case, possibly, you have more than one molecule that is asymmetrical, I am going to tell you how to differentiate between them, which one is the highest, which one is the next highest, etc. But for now, I'm just going to keep focusing on my particular problem. So the asymmetrical molecule is number 1, highest. And then of my symmetrical molecules, how am I going to distinguish them from each other? The next variable that we're going to take into consideration is the depth of the color. So for my symmetrical molecules, I'm going to kind of make like a little tree diagram here. A molecule that has atoms that are all white, so there's no color coding, no shading at all, that is going to be the weakest. Molecules that have that kind of faded color, like I see down here, faded coloring, that's going to be the next weakest. And then the molecules that have the bright colors, they are going to be the strongest. So for my symmetrical molecules, the ones that have no color, this one and this one, these are like the ultimately low, weak ones. And I don't have any faded color ones of my symmetrical molecules, but I do have this bright one. So this bright one, of these 3, this bright colored one is the strongest. So that's going to be my number 2. And then these ones with no color, they are going to be my weakest. Now, how am I going to distinguish them from each other? Smaller the molecule is, the lower or weaker its IMFs are, and the larger it is, the stronger the IMFs are. So in general, symmetrical molecules that have no color at all and are small, these are the molecules that have the lowest or weakest IMFs. Symmetrical molecules with no color and that are small, those ones are going to have the lowest or weakest intermolecular forces. Now this idea with the colors, we can translate that to everything else here. So if you had two symmetrical molecules that both had faded colors, the smaller of these two would be weaker, the larger would be stronger. If you had two symmetrical molecules that both had bright colors, then the smaller of those two would be the larger. Now, what if in your problem you had more than one asymmetrical molecule and you had to distinguish them from each other? What would you do? In that case, you would just apply this exact same flow chart as well. Let's see if I can actually squeeze it in here. I'm going to have to move this. I'm going to have to move this. And then rewrite this highest or strongest down here. So as we go from the lowest intermolecular forces to the strongest, kind of looks like this. The ones with the strongest intermolecular forces are going to be the asymmetrical molecules that have really bright colors and lots of atoms. And in general, this right here is your flow chart going from low to weak, or from low to high, and from strong to weak. Good luck.